Hi everyone, I am Ajir and today I am with you with another subject which is the line integral of vector field. Part 2 is specified to line integrals for the vector field. To understand better the concept, I have considered this figure. Here we have a vector field which has shown in blue and red colors. And we have also a curve which in under this vector field. If we consider that when we moving along these curves, so in every point this vector, these vectors as a force affect on our moving. It depends on in which direction the vector field be. Here I am moving counterclockwise, but the force is exactly in the direction of me, with me, and so it is positively affect or work on me. But being inverse, the opposite direction, so it was negative. Consider that if we hike over a mountain, the gravitation, if we consider as a vector field, so this force, it prevents us to move up. But if we come down, so this gravitation help us and it will be positively works or affect. So if I want to compute the line integral, which is exactly the work done by moving along the curve, so maybe be positive or sometimes be negative. Depends on the angle between the force and also our direction. Here if we see that direction is this, and if I consider the force here be in this direction, so the force and the tangent vector, which is exactly r prime, has the angle together theta. So I have to consider for the work done the dot product, because if we go back to the definition for the work we had before, we have the definition for the work if we suppose that f be the vector or the force and displacement be s, so the work will be defined by f dot ds. It means that norm f, norm s, and cosine theta. If I use the vector as p and q in Cartesian of x and y or in two dimension, so s be also the displacement dx and dy, f dot with s, it means that p dx plus q dy. So the definition here for the line integral, it will be by considering f as a continuous vector field and c be a smooth curve over interval a and b. So the line integral of f along c will be defined by f dot dr or f dot tds. Exactly t will be r prime t, but for the scalar function we were using the norm of r prime t, because in that the theta between the work or force, which was a scalar, and the direction was same, and cosine theta actually was 0, because if you consider one car which moving along a street from the point A to B, if I want to consider the work will be F only multiply in AB or distance here. So it means that they cause, because the direction of F and ds was same, because F multiply in ds in cosine 0, which was 1. Let's we go to example and see how we can compute the work done by a force over a curve which be vector field. And this theory presents another form of the line integral for the vector field F over curve C, which is equal to P dx plus Q dy plus R dz. And properties of vector line integrals is if we have two continuous vector fields over a curve which is smooth as C, then the integral of f plus g over c is equal to summation of two line integrals over each of the vectors f and g. And also if we have a constant k which is multiplying the vector fields, can come out of this integral. And also the three numbers is very important, which related to the orientation of the curves. And if we want to get the line integral over the minus c, opposite of the direction of curves, so the integral will be equal to minus integral of f over the curve c. And also the last one is if the curve C be union of the curves which are piecewise smooth. In order to get the integral over C, we can get the integral over the summation of the line integral of f over each of the curves, each piece of over each piece. Let's go to example. We want to evaluate the integral of y2 dx plus x dy, where first for a c equal to c1, the line segment from this point to 0 and 2. So if we consider the integral y2 dx plus x dy, so p is y2 and q is x. This is the vector field f, and which have dot product with dr. dr is dx and dy. So here c1, which I want to present as a line segment, so we need to find the for this line, every line segment we can define by two options. First, we can use as the line y minus, if I consider 0 and 2, y minus 2 is equal to m, which is 2 minus minus 3 is 5 over 0 minus 5 is 5, multiply in x minus 0. So the line will be equal to y equal to x plus 2, minus 2 is coming to right side. So we have this one. So for C1 we can write as a parameterized curve T and T plus 2. T change from because it is x, so will be 0 and minus 5. Let's try 0 and minus 5. If I put 0, I will get 0 and 2. It's this point initial. And if I put minus 5, I will get minus 5 and minus 3. So this is for C1. And now we can get the integration according to the formula f composed with r1t multiply in derivative of r1t dt over t, which is between actually here first minus 5 and 0, because minus 5 sorry is minus 5 is less than 0, I'm sorry, here we have minus 5 and 0. So between minus 5 and 0, minus 5 and 0, so we can write minus 5 and 0. F is y2 and x, so instead y I can write t plus 2, so t plus 2 power 2, and x is t. Multiply in r prime, so I get derivative of r1 is 1 and 1 dt. So we can multiply each other. We will get t plus 2 power 2 plus t. Then we can get integration respect to t, and easy you can get this integral t2 plus 2t 2 plus 4t with t will be 5t plus 4, which will be 1 over 3t3 plus 5 over 2 t2 plus 4t. T change between minus 5 and 0. So first I replace 0 instead t. I will get 0 minus, then we put minus 5 instead t. We will have here minus, will be multiplied, minus will be positive. 1 over 3, 5 over 3. And minus, here minus 5 will be positive. With 5 will be cubic power of 5 over 2, and plus here minus 4 in minus 5 will be positive 20. So here I have factorize from 5 over 3. 1 over 3 minus 1 over 2 is 2 minus 3 is minus 1 over c plus 20. So here we will get 5. Denominator is 6, so minus 5 3 plus 120, so here is 125, which minus 120, so I will get minus 5 over 6. For another one we had same, here it was the arc of x equal to 4 minus t2 from this point to this point. Actually it is same, just parameterization, which we can here write as c2. So for c2 I write r2t equal to, as y is equal to 4 minus t2, 4 minus t2, so x equal to 4 minus t2 I consider yt, and x will be 4 minus t2, and t is y between minus 3 and 2. So we need to derivative of r prime 2, which will be minus 2t and 1. Now we can compute vector field line integral of this vector field. Vector field was y2 and x. Instead y we can write t, and instead x we have 4 minus t2 dot product with this norm, this derivative, sorry, 2t and 1 dt. T between minus 3 and 2 will change. So here we will have this multiplication from minus 3 to 2 integral, and 2t in minus 2t is minus 2t cubic plus 4 minus t dt. So we can get integral minus 2 over 4 is minus 1 over 2 t4 plus 4t minus 1 over 3 t3. T change between minus 3 and 2. So here 2 power 4, so we will get minus 2 power 3 plus 4 multiply in 2 is 8, so this will go minus 1 over 3 to power, so we will 8 power 3 minus, we will put minus 3, minus in minus is positive, but with here minus we will get again positive, 3 power 4 over 2 minus 4 in minus will be positive, minus with minus positive, this minus is again minus, 3 power 2 is 9, 12 minus 9 is 3, and here we have minus 16 plus 81 over 6. Here we have 3 power 5, and here 3 multiply in 6, 18. 18 minus this is 2 plus 3 power 5 over 6, which will give us, we have 2 plus 2 for 3 over 6, which give us 2, 4, 5 over. Let's compute now with Maple software. If we go back to Maple, here we can write as, let's restart. And for the vector field, actually we use with vector calculus, V capital again, and C for calculus will be capital, and I put 2 dot instead semicolon to don't run and show the results. And for the line int, here we use again capital for first line, and int also I will be capital. Line int, here we use the vector field, and here we should define the coordinates, and I write set coordinates is Cartesian, and the Cartesian we x and y. If we have in 3 dimension, we are in 3 dimensions, so we use x and y, and here for the line int, I use the capital for line, and I again for int. Before, when we was using for the scalar function, I was small, and here was with students. Line int of the vector field, I use vector F capital, and vector field actually was y2 and x, y power 2 and x, and here we have to define the path or the line. The first we had here, if we come back here, we had the example, we had the line segment from -5 and -3 to 0 and 2. Let's say copy 2, and now we can see. So for this, we had this line segment. I can use line again capital, and for line we have 2 points. It was -5 and 3, and 0 and 2, sorry, here, and 0 and 2. So here we can run, let's check here, run this for vector field, here for the line, and this. So that's the problem. Okay, sorry, here it was -3, it was minus. Again we run, and we get -5/6, which same as our result before. And for this arc length, we use again this line just in pad. I copy here and paste. Just here instead line we have the pad. I can write pad. Pad is defined by the vector was 4 minus t2 parameterized, and t change, the y change between -3 and -3 to 2. Now we can run this also, and our answer is 245/6, equal to previous result. Here I want to notify you by one question why we get -5/6 for the line segment, and the positive for the line integral over this path 4 minus 2 and t. In order to understand this, we need to sketch the vector fields. So let's we continue and sketch every of this line integral over different curves in same diagram. So in order we need to use with student vector calculus and also the program with plot. So I will add with a student vector calculus and also with plots program to this, with plots. Let's say use the font bigger 18 for that. Here I don't want to run, just I put 2 dot and I copy and paste both of this line integral here. Here I put the name as M1 for the first one and M2 for the second, and I want to get the output here for the first one and the second one also. So here I will add comma output equal to plot, and for this also comma output equal to plot, and here I use the 2 dot, and here I don't want to get drawn for this, and then I want to display in same diagram, so I use the upload of what I want to display, M1 and M2 together. Now we can run it, and as you see here we have this line and this pad together in same diagram. Let I make it bigger size and see. If you come to this part, you will see that, for example, in this point, if I consider the tangent vector over this curve, it is in this direction because we are moving from this to this point 2. So again, against of that, so also parallel with that, the vector field as a force, it is in this direction. It means, let's say use the one in this direction, in this direction. So this tangent vector and this has a theta angle between 2 less than 90 degree. It means that the cosine of theta will be positive. And also for another point, if I consider here also this, we have the tangent vector in this direction and the vector field also in this direction. So again, we have the theta less than 90 degree, which give us positive results. But for this line, if we come, for example, for these points, we see that if you come here, you will see that the vector field, it is in this direction. But the slope line, it is here, which give us the angle between two more than 90 degree, which give us negative answer. So it means that the dot product between the force and the dr derivative of the curve over slope, it's important, or the tangent vector, is important in calculating the line integral for the line integral over the vector field, not a scalar function. So thank you for your attention. Hope this series of video was useful for you. Be always blessed by God.